long duration, far from Earth, in extremely harsh environment for humans. Yearning for family and friends left on Earth would be an impactful psychological discomfort for astronauts. That is why a lunar habitat which would soothe the effect is needed. The Lunar Lighthouse project is driven by the need to develop a system of protection against radiation for the surface lunar base, which would allow for more freedom in shaping the base structure. Building a vertical structure would overcome the obstacles given by the dust contamination floating above the surface raised by engines and mechanical works. From a psychological point of view, it is very important for the astronauts to have possibility to look outside the base, but from technical point of view, placing windows in space habitat is very hard because of the protective aspects. I'm trying to resolve this issue, introducing a system that will allow for a daylight to pass inside the base structure without any losses on protective capabilities. Because of the payload restrictions, local materials should be used when and where possible. Thus, the main material for the rigid radiation protection shell is lunar regolith. However, because of the angle of repose, even if it's bigger on the lunar surface due to the lower gravity, any kind of soil, whether if it's sand, earth, or regolith, is not strong enough to act as a construction material in and of itself. So how we can protect lunar regolith? Soil strength almost completely depends on internal friction between the soil particles themselves. To avoid sliding, the frictional force can be considered the shear strength. The more friction force, the more strength against shearing. The shear strength of soil depends on the internal forces. However, unlike other materials, soil have an infinite number of potential sliding planes all at once. With the use of geosynthetic material to reinforce the soil mass, it is possible to build a stable structure with smaller amount of material used. Based on the soil reinforcement principles, freedom in designing shape can be achieved by inclusion of randomly distributed fibers, continuous stripes, or sheets within a soil mass. It stabilizes unstable slopes and helps to retain the soil on steep slopes. To ensure lateral stabilization, reinforcement, instead of being divided into separate layers, is designed as a continuous surface, climbing in the form of spiral along the whole structure. So what we can use as a reinforcement materials on the lunar surface? I propose the use of nanocellulose. It is a cellulosic material extracted from plants, animals, or bacteria. It is light, solid structure, and has exceptional strength capabilities. And in crystalline form, it becomes translucent. At the University of Texas, researchers investigated genes from the family of bacteria that produce vinegar and kombucha tea to use nanocellulose. Nanocellulose made by bacteria is easily produced and high in purity. ISA conducted experiments on a set of kombucha-making organisms inside the Expo R2 container on the ISS as a part of Biomex experiment on how organisms and their molecular structure react to the combination of unfiltered solar light, cosmic radiation, vacuum, and temperature changes. It has been proven that biofilm forming microbial communities can survive in harsh environment. They display greatly increased resistance to physical and chemical adverse conditions. And kombucha cultures, to protect themselves against the harsh conditions, releases nanocellulose-based structures. And bacteria which are producing nanocellulose are photosynthetic. It means that they're capable of producing their own food by photosynthesis process. The nutrients are synthesized from carbon dioxide and water using sunlight as chemical energy. Nanocellulose is potentially easy to harvest since its bacteria had the potential to release nanocellulose directly into their surrounding. It has been also tested that kombucha cultures are exceptionally robust when mixed with the lunar dust. Nanocellulose absorbs minerals from lunar soil, protecting the culture even better. The lunar environment consists of a hard vacuum. Thus, in order to protect humans, highly pressurized structures are required. To enable in situ production of the nanocellulose membrane, a production module would be needed. Inflatable membrane would keep the right atmosphere and conditions for the nanocellulose growth, providing water and CO2. These two structures would have to be brought from Earth, rest, can be gathered, produced, assembled on the lunar surface. And that's how the base may look like. There are inflatable modules inside, protected by the rigid regolith shell with nanocellulose reinforcement. On the top of the structure, nanocellulose protection module is placed, and it folds, when the base is fully assembled, it folds back and closes the structure. For location of the base, the Shackleton crater rim was chosen because the crater stays in shadow almost for all of the time, what makes it a good potential site for the lunar base due to the possible presence of the ice. Crater rim, on the other hand, is a site with sunlight present for almost 90% of time, which makes it peak of eternal light. With a site and a peak of eternal light and translucent nanocellulose membrane, which work as a light fiber placed all along the structure, the sunlight can gradually pass inside, having a maximum density on the top of the structure. The spiral nanocellulose has differentiated diversity. Its gradient character makes the diffuse sunlight passes into the structure in the particular manner. On the top level, the sunlight provides high luminous intensity. However, towards the bottom, less light reaches the interior. To keep the crew healthy, pressurized modules are equipped with an artificial light system imitating day-night Earth cycle. On the last floor, where there is no dust contamination anymore, the density of the cellulose layers is proposed to be the biggest, and due to the height, light would shine there at all times. Translucent nanocellulose not only would transmit light to the base, but also light up itself, making the top of the base clearly visible from the outside. During external activities, the base would become for astronauts what a lighthouse was for sailors, leading them for the safe haven. And the same concept can be also translated into Martian surface, thanks to the Martian atmosphere, which is composed mostly out of carbon dioxide, which is crucial for in situ growth of the nanocellulose. And thanks to that, we can build future human-oriented settlements on Mars. Thank you.
Thank you, Monica. Questions? There have to be questions.
Robert is not here. Okay, go ahead.
Have you looked into performance of nanocellulose materials in space, in vacuum and radiation?
So I based the project on the ISS Expose R2 mission. So reading the paper, I didn't test it myself, but yeah, so I based that. They claim that it's very, it can live, and the bacteria producing nanocellulose, they can survive in these harsh environments, and actually they produce the nanocellulose to protect themselves from the vacuum and radiation.
Is it important that the nanocellulose stays alive while it's already in the structure?
I don't think so, but I'm not really sure because I didn't have chance to make tests on them by myself, so yeah.
Phase 2.
Phase
Okay.
2.
One more.
Thanks. I was wondering if there is a way to control the growth of the nanocellulose. over time.
I think it depends on the amount of the solar light and amount of water that it has, and also it probably will be way different in a microgravity or in a 1/6 of the gravity than on Earth. But I don't know yet how to control it by ourselves. So, but yeah, hopefully there is.
Okay.
Okay. Thank you.
Thank you.
Thank you. Okay, now we'll shift to chapter 4, the final chapter of our session. We have 4 talks on terrestrial analogs of one sort or another. So, Manfred Palmer. FlexHab working module architectural requirements and prototyping for a lunar base analog. Yours is 44461.
So, welcome everyone. Thank you for attending my presentation. My name is Manfred Thalner, and I'm going to present you my work on the FlexHab working module. FlexHab, or the Future Lunar Exploration Habitat, is a project of the Spaceship ESE initiative, which was created by ESA to develop innovative technologies to support ESA's exploration strategy. I was part of the initiative last year to do the work on FlexHab, which is located at the European Astronaut Center in Cologne. My presentation will be structured into 3 points. First, I give you an overview of the initial situation, then I present my design and the prototype, and the third part will be the evaluation and the conclusion. So the European Astronaut Center, as the training facility for astronauts, is going to extend its capabilities in astronaut training by constructing a simulated lunar surface. And on the right side, you can see attached the FlexHab working module, which will serve as the lunar base, so to say, from which the surface can be accessed. The module itself in its construction has already been developed by previous Spaceship ESE members, and it's given an interior volume of about 10.5 by 3.2 meters with a quite functional shape and section, so to say, which is given as my starting point. And the requirements for the interior have been, first of all, there was flexibility. To adapt to different mission scenarios with a higher level of flexibility is required. So to adapt to future astronaut trainings, and of course the so created space should be used as efficient as possible. To meet these requirements, the FlexRack concept was developed before as well, which is basically a movable rack concept that allows different configurations within the module to open up spaces where they are needed while storing things that are not in use, similar to archive storage systems, as you can see on the left. So if we look at current space habitats or analogs right now, we do know that the confinement and the isolation do have effect on human beings, so we're investigating those effects, but also we need to develop designs that specifically address to those effects and try to minimize them as much as possible. So my part as an architect is to develop a design for the interior, specifically addressed to the FlexRack concept, to develop use cases, and further to build a prototype, which then evaluated to give design requirements for the final design of the habitat. So I'm going to explain now the interior design that I developed based on 3 essential parameters. There's isolation and confinement, the absence or different light we would have on the moon or in a simulation, and changing spatial requirements, as we don't know the exact simulations or scenarios. 3 main design measures are addressing those parameters. That is, first, the visual extension of space, the simulation of natural light to get as close as possible to our natural environment, and the changeable interior through the FlexRack concept. So you can see now the main compartment of the habitat, which is now empty, but will be equipped with technical necessities such as removable panels and rails for the FlexRack system, as well as space for cable management, which already makes the room appear quite different. And this room is then complemented with several elements, such as lighting. First, the indirect ceiling light, which not only provides sufficient illumination of the habitat, but also extends the perceived height of the room. And also the same principle is applied to the walls through creating a partial setback that is creating a window reveal area that will be illuminated through backlit translucent glass or similar material to not only create a common situation we have in usual buildings, light coming from the side, but also to extend the space horizontally. So by designing such a small space, there's a problem of visual monotony coming up. So even though you have a perfectly designed interior and something that is less crowded, as you can see, it's still, after long terms, it's always the same. So it gets boring for the brain, so to say, and this understimulating the brain can result in reduced performance of the crew. So to avoid that, the previous described design measures can also be used to add individualization possibilities through colors, through materials, or even more advanced concepts to actually simulate an exterior natural environment. Complemented with a light system in variation of light, you could also then simulate natural circadian rhythm to get an environment that is as natural as possible inside a closed volume. Also, the other way around, you could do a simulation of the lunar conditions to study the effects on human beings. The now still empty volume will be complemented now with the flex rack. So the question first was what happens in flex hab, and my part was also to see what kind of experiments will be in there, what kind of astronaut training will be done, and especially concerning the spatial requirements, as it makes a big difference if you control a rover by hand controls or, for example, through virtual reality. So based on the input of my colleagues at ESC, I was developing a configuration of racks, which then has been transformed in different scenarios to see where are the advantages and disadvantages. For example, you could arrange workstations so that communication between crew members is easier, or for technology demonstrations, you could open up space for more people attending, which would be impossible with fixed furniture. So addressing the efficiencies, to make all this possible, the racks are designed in a way that things that are currently not in use can be stored away with as little space occupying as possible through simple sliding or folding elements. So the now developed design was transformed into a prototype located at ESC, and it consists of two basic racks which can be used for storage or for different experiments, and the workstation. And that brings me to the last point, the evaluation of the prototype. So I developed several scenarios and tasks that have then been carried out by different test subjects, so to say. And just to give you an impression what has been done, different scenarios, just to see how the thing works, what is the feedback by the people, but also through individual use and following feedback questions, question and answers. So the conclusion that can be made so far on the prototype is that the movable racks have especially been helpful for construction, but also for maintenance activities. So if you can move things aside without carrying them, that helps a lot, especially if you have a habitat that needs to be maintained all the time, where wires behind walls have to be exchanged or something like that. Of course, there have also been issues that need to be improved. For example, the rail system was a pretty simple one for the prototype, which creates quite big gaps that need to be avoided in the real habitat to get more smooth surface, also for hygienic reasons. Other things that weren't actually meant to be put in the actual habitat in the first place turned out to be quite useful. For example, I used pre-mounted profiles to connect the different slides, which turned out to be very useful for mounting racks, and also if they give the possibility to mount other stuff, others than racks, tools or whatever. So overall, we can say that the developed design allows for quick spatial reconfiguration, so we can create different simulation scenarios, different astronaut training situations, and of course, through efficient design, we can get more racks inside the same space as it would be with another system. And also, the prototype has shown that the space between the racks, for example, depend pretty much on individual choices. So having an interior that is reconfigurable can also improve the comfort if we think about long-term simulations or long-term space missions. Having an environment that you can physically interact with, that you can change, that you can avoid unpleasant situations, could actually improve the habitability of future space habitats. And that's it. Thank you for your attention.
Any questions?
Well, I have a question. Yes, yeah. So, yeah, I have several, but yeah, I asked only one.
You only get one.
Yeah, only get one. The thing is, have you considered how much the whole system will weigh?
The thing is planned for the simulation, so
Yeah,
weight
doesn't
won't
matter.
really matter. I don't have the figure in mind. I did the calculation once how heavy it is, but it's quite heavy. So, like
So the
this
space application is not considered.
space application would need different materials, different construction, but the principle can be still developed in the simulation.
So my question is, you had really two aspects. One is the psychological design for psychology, and the other is the design for practicality and utilization. And it seems that the use of walls for imagery and color and scenery and so forth is not compatible with the use of wall space for work. Covering it up or hanging things on it or sticking stuff out of it, and so how do you reconcile those two?
So, yeah, as I showed in the image, the whole wall would be used for background images. Once you have racks in there, it would make sense to partially have, for example, an image or whatever. So, if you have different sections in the module or different elements, so one could be used for illumination, for example, where the racks are, you don't need any illumination, it would only be disturbing and not helping at all. So, you would need to make the system more variable and divide it in sections. So not the whole thing.
Okay. Thank you.
Okay, you have.
I have a similar question to yours. If you already have these windows / projector on the side, and you also show that there is a light on the top, which is an overkill. Why do you need that? And can you use these windows as computer screens, as magic windows, as light sources? Virtual windows for multiple purpose, and just simplify the whole thing further.
But you cover it.
Then you segment it and then cover it.
Okay. Yeah.
So yeah, so both systems, like fully, like I showed, is maybe you're right, maybe an overkill, but yeah, you can also imagine that it's not the whole completely feasible simulation with all the background. So maybe it's just light, maybe it's just colors. And also having only the light from the side, as we talked. If there's a certain area where there are only racks like in a row, then you need something else. So you have, again, the same thing. So you need sections. Probably on one section you have ceiling light, and on one section you have. Yeah.
Okay. Thank you. I think
Sorry, guys. You need, yeah.
we'll have to do other questions after the session is over. Thanks
Thank
much.
you.